Welcome back. This is Laylor's Maid. Let us rejoice and be glad in it. In this video here, I'm going to talk about physical science week 31 topics, mostly about waves, general ideas about waves, pitch, frequency, decibels, speed of a wave, etc. So anyway, so what's a wave? A wave is just a transfer energy. If energy moves from one place to another place, it might do so through a wave. All right, so you drop a pebble in a pond and it creates a wave, and the wave transfers energy that the pebble, when it hit the water, spreads out. So most waves need something to transfer the energy. So here on Earth, most of the waves, I shouldn't say most waves, many of the waves we're used to are waves that are going through a material. However, light does not need something to go through. And that actually baffled scientists for a long time. Like, well, how does the sun's energy get to us? Isn't there something out there that the light has to travel through? So light's pretty much the only thing that doesn't need anything to travel through, but everything else does. All right, there's two different types of waves. There's transverse and longitudinal. A transverse wave is what you probably think of as your typical wave that you see, because as the wave goes to the right, the matter goes up and down. So a transverse wave makes the matter move perpendicular to the path of motion. So when you think about a transverse wave, it's going to make the wave's going to make the matter move up and down as it goes through. So again, here's your typical wave that you think of when you think of a transverse wave. You know, the wave's going through it, and the matter goes up, and the wave goes down, up and down. So another wave is a longitudinal wave, and this one, the motion is actually parallel to the wave motion. And so it's more like an accordion or a slinky that's vibrating back and forth. And so this is actually how sound is, because what happens when I'm talking and when you talk is we have our vocal folds that are like vibrating, and as they push out and pull back, it punches up the air and pulls back and making it a high pressure, low pressure, high pressure, low pressure. And so and that's what we see. That's what a longitudinal wave is. Actually, it's not a transverse wave. Now, even though many waves are compressional waves, we don't like to look at those things as much as this. And so usually like a computer will change it so that it looks like a transverse wave. Like even a heart monitor is going to be measuring like a wave through the heart when it's like beating, and it's going to make it look like a transverse wave because we understand, we can see a transverse wave and see what's going on. So again, this is the idea of like what's happening with the tuning fork, also with our vocal folds. To make a wave, if something's vibrating, we smack the tuning fork and it vibrates, and as it goes back and forth, it makes this high pressure where the wave is pushed out together and it pulls it back. And then that vibration continues to travel through the air. And so as it vibrates, it makes these places that are high pressure and then low pressure and high pressure, and the wave just permeates, moves through space. It's just a picture of a loudspeaker, which is the same thing, just like a vocal folds. All it does is it pushes the air out, pulls back, pushes the air out, pulls back, and we have this high pressure, low pressure, which we can interpret as different pitches. So now parts of the wave and other stuff related to it. So the amplitude is going to be how much the wave makes the matter move. How much does the wave displace the matter? That's how high it's going to be. The crest is going to be the highest point, and the trough will be the lowest point that the matter is moved. Normally we think crest being up and trough being down. And so looking back at our longitudinal wave, our transverse wave, we'd say that, okay, the amplitude is just how much did the matter move up and down. And this top place here is going to be the crest. This bottom place down here is going to be the trough. And the amplitude is how much it actually moved by. The frequency is going to be how many times per second it goes up and down. So as the wave travels through, how fast does it make the matter vibrate back and forth? The frequency is how many times per second does it actually move up and down. So like middle C on the piano, it's like somewhere in the 200 hertz range. That means that that string vibrates over 200 times per second. Then the period will be how long it takes for just one vibration. How long does it take for that string to move back and forth just one time? And so lots of big tall buildings sway back and forth. So for example, the Sears Tower has a frequency of about 1/10. That means that in 10 seconds, it goes down and back one time. So it sways slowly back and forth. So all the words you mentioned so far, with a couple new ones here. Period, how long it takes to go from crest to crest. How long does it take to go through one cycle? Crest, that's the high point. For a longitudinal wave, that would be like the areas of compression where it's pushed together. Troughs or low points for a longitudinal wave, that's like the rare spot where we have low pressure. Midpoint, this is just basically saying where was the matter before the wave came in. Amplitude is going to be how high it's been displaced, how far it's moved from where it's supposed to be. Wavelength, that's how long the wave is in meters. And frequency is how many times a second does the wave actually go up and down. So a useful equation for you will be this one here, how period and frequency are related. Period equals 1 divided by the frequency. So period is going to be in seconds, frequency is in hertz. So a sample question for this would be, let's say we have a tuning fork with a frequency of 100 hertz. What would be the period of the wave? And the frequency tells us how many times per second that tuning fork is going to vibrate back and forth. So bong, you hit the tuning fork, it's going to vibrate back and forth. We're saying it's doing 100 times per second. The period is how long it takes to do one time. So our equation, period equals 1 divided by the frequency. We're looking for the period, 1 divided by 100, which is the frequency. It's 0.01 seconds. So every 100th of a second, that tuning fork is going to vibrate back and forth. Go another way, let's say we have a guitar string vibrating and we have the period. The period is how long it takes for it to go down and back. So think about plucking your guitar string. What's going to happen is your guitar string is going to go to the right, go to the left, and we're saying that it goes through the whole cycle in 200ths of a second. What pitch would you hear? What frequency is going to be generated by the guitar string? Same equation, period equals 1 over the frequency. This time we have the period. So 0.02 equals 1 over f. We got to rearrange for the frequency. So we're going to take 1 divided by 0.02 and bring the f back up on top over here. So that means the frequency is 50 hertz, 50 times per second. That wave is going to go down and back. Another important equation for us is about how fast waves moves. And so this equation here, velocity of the wave equals the wavelength. This is that funny looking symbol here, that lambda. This is the wavelength. And the frequency is going to be the hertz. So the speed of the wave depends upon the wavelength and the frequency. And these things are inversely related. So if one goes up, the other one goes down. I should make a quick note. There's a common misconception people have, and that is that different pitches travel different speeds for sound. That is not true. So most people have this idea that like a high pitch played on a piano travels faster than a low pitch played on the piano, or like an instrument that plays a high note, that wave travels faster than a note played by a low note. That's not true. If that was true, then going to a concert would be really hard because then not all the waves would hit you at the same time. And so the speed of pretty much all the sounds that you hear is the same. All that changes is your wavelength and frequency. So a high note would have a real high pitch, which has a small wavelength. And the low notes would have a very long wave. So when you think about your piano playing high notes and low notes, the high notes on the piano, they're going to have very, very short waves. So the wavelengths might be like a couple centimeters long only. And the low notes, they're going to have waves that might be like bigger than your room. They might be like 10 to 15 meters. So a couple sample questions. Say a wave has a wavelength of 2 meters and a frequency of 150 hertz. What is the speed of the wave? So our equation, velocity equals wavelength times frequency. We're solving for the velocity. What is the speed? So our wavelength is 2 meters. Our frequency is 150. 2 times 150 is 300 meters per second. A wave has a frequency of 600 hertz, moving at 300 meters per second. What is the wavelength? So now we're looking for the wavelength. We're going to have to rearrange for lambda here. To do that, we're going to take the velocity divided by the frequency. We're going to take this frequency, bring it down over here, velocity divided by frequency. So 300 equals question mark times 150, 300 divided by 150, that'd be about 2 meters long. So, all right, other cool things. So think about when something's moving, it makes a wave of air too. Just as you run through the, if you're going to track meet, you run, you're creating a high pressure area in front of you, which makes sound. You can't be stealthy and be fast because the faster you move, the louder you become because you're making a higher pressure, a higher amplitude sound wave. Eventually you travel fast enough, you get to the speed of sound, which is Mach 1. At Mach 1, you're moving at the speed of sound. And so when you make a sound wave, it gets added right to the last sound wave and gets added together. So speed of sound is roughly 340 meters per second at room temperature. So it's pretty fast. It's 700 miles per hour-ish. So another cool thing about sound waves is the frequency can be distorted, can change if you're moving. And so when an ambulance is approaching, you hear a higher pitch than when it's leaving you. This is known as a Doppler effect. You probably are familiar with the idea of like Doppler radar. Doppler radar basically is the idea that we can send out a wave and see if the wave changes pitch. And if the wave changes pitch, then we know something's moving towards us. So like if there's a storm moving in, we can use Doppler radar to see how fast the storm is moving. Police radar does the same thing too. You know, they can just send out a wave and see how much is distorted as you move back. So anyway, the general idea is if something's moving towards you, you're gonna hear a higher pitch than what's actually being produced. And if something's moving away from you, it's gonna be a lower pitch. So next time you're stopped at a train track and waiting for the train to come, you'll hear a high pitch as the train approaches, you hear a low pitch as the train leaves. Or if you go to the swings and I got 4 kids, if I'm at the swing set and I'm pushing the kids, if they're screaming with glee on the swings, as they come towards me, I hear a higher pitch, and as they move away, I hear a lower pitch. All right, so when waves run into matter, they have a couple different options. They have pretty much 4 things they can do when they run into something. So they can be absorbed, reflected, refracted, or diffracted. So to be absorbed means that the energy that hits the medium just gets absorbed. It's just taken in. And so if you've ever been in a basement that doesn't have carpet, it's very echoey. When you make a sound, it echoes in there, and the energy seems to stay in the air for a while. But as soon as you carpet the downstairs, then what happens is you no longer hear that echo, because carpet tends to absorb sound waves. The sound waves kind of get stuck on the carpet, and you know that's where they go and they're done. So you can also think it's like acoustics. So you know, how does the room acoustically work? Is the energy being absorbed by the walls? Is it bouncing around in a bad way? Is there quiet spots? So you know, you might have even heard like quiet rooms where like you go into the room and like the whole walls are padded, so everything's really quiet in there because all the energy gets absorbed. Reflecting just means that the wave bounces off actually. This is no different than like thinking like a mirror and seeing yourself. The light hits the mirror, bounces off. This is basically like how echolocation works, how sonar works. Something sends out a sound wave, we listen for it to bounce off something back to us, and then we know something's there. So, and this is how like bats, dolphins, they hunt. They basically make a noise, they listen to see if the noise bounces off something close by, and if it does, they go get it. All right. So, although we should mention that, you know, some animals that are the prey actually have ways to counter this too. Like, for example, there's a moth that, or you might have wondered, why are moths like fuzzy? Why are they so fluffy? It's because it's like carpeting their skin. They basically don't bounce off the wet energy very well. So when the bat sends out the wave to try to eat the moth having like fuzzy wings makes the sound not bounce back as much. It absorbs a lot of the energy to make it harder to find them. So refraction is the idea that a wave can go through something, and so instead of bouncing off it, it travels right through it. Usually when you travel through, though, you bend a little bit. And so refraction is the idea that a wave goes into something and bends as it passes through. Think like a prism, like, you know, light comes into a prism, and then all the waves kind of spread out and make a rainbow. Also, waves could just bend around something. Diffraction is the idea that a wave can just bend around something. So think about like going to the lake and there's a rock in the lake, a big rock, and you throw another rock in, it makes a wave, and as it goes to the other thing, it bends around it. So this is why like you can hear me inside of another room, because my sound waves they'll diffract around the house and spread out and just travel around corners. So diffraction is the idea that we just bend around things. Waves can just do that. So again, here's some pictures. Diffraction, if we had some bear in the wave, we have some wave coming towards it, the waves just bend around it. Reflection just bounces right off. Refraction, we travel through it, but then we kind of change direction as we go through it. Waves can also add together or cancel out from each other if you have multiple waves. So constructive interference is when waves hit each other and add together to make it louder, all right? Destructive interference is when waves hit each other and cancel out. This is actually really an important technology, especially when it comes to like noise cancellation devices. Destructive interference is the idea that the device hears a wave and they send down a counter wave to basically destroy the other wave. And so if one thing has a crest, the other thing sends out a trough and they cancel out, that's destructive interference. And that's noise cancellation technology. Any place where you have no noise then, where you're canceling it out, is considered a node. A node is where like basically the waves cancel out. And so a node means no noise. An antinode is where it gets really loud, where like the waves hit each other and actually get louder. So I have some pictures down below, I think. Maybe not. Okay. So reflection, waves bounce off. So when you think about reflection, think like sonar. Like the wave's just going to hit something, bounce back. Refraction, waves are going to travel through it, change direction, think like a prism, bending the angle. Diffraction, the wave just bends around it, so it just, the energy is going to spread out around the material. Absorption, this is where the waves just get absorbed into the material and the sound stops, it dies out. So think like carpet flooring. Constructive waves add together. An antinode is really loud. Destructive interference, waves cancel out. A node, no noise. So I put it in the wrong spot. Here we go. So constructive, destructive interference, blue wave, green wave. They're going opposite directions. The blue wave traveling to the left, green wave traveling to the right. So the red line is what actually we see then. So right now, where the green wave and the blue wave are, they have completely canceled out because the green and the blue are opposite each other. Again, this is an example like complete noise cancellation. There is no noise now. But as the waves move past each other, what happens is the added waves together come together and we get a different thing. So on the next line here, as the blue moves a little further and the green moves a little further, now we actually have the red up a little higher because both the blue and the green are above here, and so it adds up above this. And here, at this location here, green and blue are below this line, so it adds up below. Over the course of the waves moving through each other, we end up having places that don't move at all. The places that don't move at all ever are the nodes. So as these waves pass through each other, always at this location, the red line has not moved because the blue plus green equals 0. And we consider that a node. But at some places, as it goes through, it gets really big and it might stay big. So this is considered an antinode where they add together and get really big. So we have this pattern of node, antinode, node. And so if you ever watch a show like The Big Bang Theory, you know that Sheldon goes to the movie theater and he's like trying to find the best place and he moves around and he's like, he moves to different spots, seeing where is it the quietest, where is it the loudest, because inside of a movie theater, you're gonna have some interference being generated. All right, next thing, decibel scale. The decibel scale is how we talk about how loud something is. So it's a measurement of how loud that sound wave actually is. It starts at 0 and it goes pretty high, although, I think the highest sound somewhere around like 190 decibels, but it's not coherent. It's just really loud, lots of energy in the air. So if this is a log scale, what that means is every single bell is actually 10 times louder. Every 10 decibels is 10 times louder. So there's a huge difference between 10 decibels and 100 decibels. Other things too to be aware of, infrasound and ultrasound. This is like talk about what we can actually hear. So what do we hear? Humans typically hear between 20 hertz and 20,000 hertz, although you might have some hearing loss, or you might be able to hear a little better when you're younger. But generally, humans, if it's vibrating less than 20 hertz, we won't hear it. If it's above 20,000 hertz, we can't hear it. But in between that zone, we can hear it. So again, the decibel scale is a power of 10 scale. So that means every 10 decibels is 10 times louder. So here's just some examples. So, and we should remember that these things here are powers of 10 difference. So if we compare 140 to 120, this is not just 20 times louder, it's 2 10s. So it's 10 times 10, 140 versus 120, it's 100 times louder. So we should mention too that the threshold of damage to the hearing starts somewhere around like 80 to 90 for prolonged time. So if you're listening to 80 decibels for like 8 hours, that's probably gonna have some long-term damage for your ears. All right, and as you go up higher and higher, the time that you can listen to without permanent damage is less and less. Although we should mention that your body is able to protect itself slightly. So for example, if you go to a rock concert, what happens is your eardrum will actually be pulled away so it stops banging on the drum inside yourself. So you can think of it like, the sound is hitting your ear, but your ear has basically pulled the drum away so it no longer hammers. That's why sometimes when you leave a rock concert, everything's really quiet because your body is still protecting itself. So anyway, again, big ideas, it's a log scale. The lowest one, 0 decibels, that's the threshold of hearing. That's a really tiny number. The threshold of hearing is 1/1,000,000,000 of a watt per meter squared. That's hardly any energy, but again, that should make sense if you think about it. Our God's pretty awesome. He made our ears very sensitive because even as I talk, everyone in the room could hear me, and it's just a couple little vocal folds vibrating, and you interpret that little vibration as it spreads out through the air to be noise. And it can be loud. You know, someone could scream and it's really loud. It's like, whoa, it's just a couple air molecules hitting my eardrum, and it's, you know, might be piercing you. You're like, it's loud. Anyway, so to help us illustrate this idea of the power 10 scale, let me just do a couple of sample questions. So how much louder is 9 bells than 6 bells? So since again, and deci is just a prefix, so we took off the prefix. So 9 bells, 6 bells. So every 1 bell is 10 times louder. So 9 minus 6, that is 3 louder. But those 3s are actually zeros. So every single time you go up by 1 bell, it's like adding a 0. So that means that this would be 1,000 times louder, okay? Because 9 bells is 90 decibels, 6 bells is 60 decibels. So we've gone up 3 times. 3 tens, which is every single time you go up by 10 on the decibel scale, is 10 times louder. How much louder is 80 than 60? Again, 80 minus 60, that's 20 decibels. That's 2 tens. 2 tens, every single 10 is 10 times. 10 times 10, that's 100 times louder. Last things here, we got a couple notes about other things related to sound quality. So when someone makes a noise, when I say something or I sing something, my voice is unique, your voice is unique. Sound quality is the idea of like timbre, all right? It's why a trumpet sounds different than an oboe. That's because I don't just produce one pitch. My voice will produce a fundamental note, which is the lowest pitch, but then I have multiples of that, which are overtones. And then you get a whole bunch of combinations of overtones, and you get a different quality of the sound. The pitch stays the same, meaning like, you know, if a trumpet plays middle C, oboe plays middle C, they play the same pitch, and you would recognize them the same pitch, but they still sound different because of the overtones that are being generated. Other things that can be heard are things like beats. Beats are like when something is like almost the same pitch, but not quite. And so you hear this irritating beat pattern as you listen to it because it's like not quite right. So if you tune a guitar manually, what you do is as you try to tune it, you're listening to see, do I hear a really irritating beat pattern? So here's an idea of like a beat pattern. If one wave is 40 hertz, one wave is 50 hertz, if we add these together, sometimes like right here at the beginning, it adds together, and sometimes they cancel out. So here, this one plus this one, this one's low, this one's high, cancel out. And so we have these constructive and destructive interference, which again produces this pulsing beat pattern. It just keeps beating and pulsing. So, and that's things that are irritating to listen to. All right, in review, the last things we talked about: infrasound, less than 20 hertz, ultrasound, above 20,000 hertz, beats. If 2 waves are almost the same note, but not quite, they create a beat pattern. It's kind of like if you're at a stoplight and you're turning left and you watch your blinker and you watch a person's blinker, you watch your blinker and someone else's blinker, sometimes they line up, then they get out, and then they line back up again. That's beat patterns. All right, the fundamental note is to be the lowest pitch produced. Overtones are just multiples of the fundamental. So I should mention that there are multiples of it. So if you're singing 100 hertz noise, your overtones will be multiples of 100. So you produce like 200 and 300 and 400 hertz. Timbre is just a fancy word to describe sound quality, saying why did this thing sound different. Mach, speed of sound. Sonic boom, when traveled real fast, fast speed of sound. And decibels, how we talk about loudness. And every 10 decibels is 10 times louder. God's peace.